Okay, hey everybody, this is part 2 of lecture 6. This is actually my second time filming it. If you follow me on YouTube and you saw my previous upload, there was a bug and I decided I would redo it. So that's also why it's much darker in the room. It's now 6 o'clock in Washington, D.C., and there's actually quite a bit of snow. I'm looking out the window and the trees have all turned white, so hopefully I'll be able to get home tomorrow. So let's begin. So in this part, part 2, we're going to talk about the device space transform, and we're going to do some more math primer stuff. So this is some context. Here's the game plan, and there's a lot in this slide. The game plan is we're going to calculate 3 transforms: camera transform, view transform, device transform. And then we're going to take these 3 transforms, each of which are 4x4 matrices, and we're going to compose them together to make one matrix. So conceptually, we're taking a point, P, and we're multiplying it by the camera transform, and then that by the view transform, and then that by the device transform, and we get some new point P prime. But instead, we'll compose the 3 to make a new matrix M. So we'll say M equals CT times VT times DT, and then we'll do P times M equals P prime. So these 3 transforms, camera transform, view transform, device transform, are going to be the subject of the rest of this lecture. And in fact, I'm going to do device transform in just a moment now because it's really simple, and I'd like you to see a simple transform. Camera transform is going to be harder, but we're going to derive it. We'll derive it by calculating the camera frame and then deriving the camera transform from the camera frame. For the view transform, I'm actually going to refer you to Ken Joy's graphics notes, and there'll be a link for that in a second. It's also on the class webpage. But we'll still explore the view transform and how it works. So the idea is that we're going to have some triangle out here. In fact, let me just drop the triangle in. That's inside the view frustum, and it has 3 points, and so we'll call these points A and B and C. And then for each of these 3 points, we'll calculate A times M to get a new A prime, and B times M to get a new B prime, and C times M to get a new C prime. And then we'll have now our triangle will have new vertices. No longer will its locations be A, B, C. They'll now be A prime, B prime, and C prime. And A prime, B prime, and C prime will all be in device space. And so then we'll be able to use our previous code from 1D to rasterize the triangles. Okay, I just got a phone call, but I'm screening it. So that's the game plan. We make these 3 matrices: camera transform, view transform, device transform. We compose the 3 to make a new matrix, and then for each triangle, we're going to take its 3 vertices and apply the matrix to get new vertices, and then we can apply our 1D code. So that's what this slide says, and that's the game plan. So let's look at the device transform, and it's in modified device space, meaning that here it says from 0 to width in x, 0 to height in y, but it's also going to go from -1 to +1 in z, and so we're keeping a z component here, and that should hopefully feel comfortable to you after doing project 1D. So we're going to start with data that's in image space, and that will be the result of our view transform, and then we're going to take it to device space. Did I get that right? Yes, view transform, the second transform. So camera transform, view transform, device transform. And so we're going to start with triangles that are in this space, and we're going to transform them to be in device space. So what does this transform look like? We're going to start with a vertex of a triangle. That vertex will be at some location, x, y, z, and we're going to transform it to a new location, x prime, y prime, z prime. Of course, this x, y, z is in image space. And then the x prime, y prime, z prime should be the following. X prime should be n times x plus 1 over 2, and I've expanded it out to be nx over 2 plus n over 2, and y prime should be m times y plus 1 over 2, which is my over 2 plus m over 2, and z should be unchanged. And this is for an image that has n pixels in width and m pixels in height. It turns out this is actually maybe a little bit of a problematic thing. How I have it formulated here is that we're scaling it by n in width and m in height, and if n does not equal m, we're going to end up with something that's fatter or skinnier than it's supposed to be. I'm not going to worry about that issue. In practice, actually, people typically take one of these two, and then we'll use n in both spots or m in both spots. So here's our formulation, and let's look at how it works. If x is at -1, then it's going to take us to 0 in device space. And so x is -1, -1 plus 1 is 0. 0 times n, 0 divided by 2 is 0. And so this is going to take us to 0 in device space, and similarly, if y is 0, then it will take us to 0 in device space. And then if x is 1, or if y is 1, then it should take us to the width or the height. And so here, if x is 1, we get 1 plus 1, which is 2, divided by 2, and then 2 times n is n, and that's the width, and similarly we get m in height. And so these are the desired points. X prime equals, and you see I have this formulation, but I've expanded it out so we can see how it should work in matrix form for x prime, y prime, and z prime. And so then here's our matrix. If we take the point x, y, z, 1, and when we talked about adding this fourth point on Thursday, so-called homogeneous coordinates, and I'll talk about that again actually in a few slides. But if we do that and then we multiply this, we get x times n over 2 is nx plus 0 times y plus 0 times z plus n over 2, and that gives us our first term. And so the output would be nx over 2 plus n over 2 for the first coordinate of the output point. If we do it with y, we get y times m over 2 plus m over 2. Z becomes z, and 1, that fourth coordinate, stays 1. So this is actually a pretty easy transform, and this is our third transform, which is the device, the modified device space transform. Again, modified because we have a z component. So this will be one of your three matrices, and hopefully the easiest one to do. The rest of this video is going to be on math prep, and again, I want to direct you to Ken Joy's graphics notes. It won't so much be for this section. It doesn't talk about, for example, I'm going to tell you about norms and dot products and cosine and cross products, but it will tell you a lot about the camera transform and the view transform. Really great set of resources. There's also a link to it on the class webpage. Okay, so the first thing is what is the norm of a vector? So the norm of a vector is its length. It's denoted with these vertical bars. And so here's a 2D example. If we have a vector A that has components a dot x and a dot y, then here's the vector at a dot x, a dot y. It's going a dot x out and a dot y up. And so then the norm is just the length of this vector. In 2D, that would be the square root of the sum of the components. So just the hypotenuse of a right triangle. And 3D, the norm of a vector is the square root of the sum of all three components. So the norm of a vector is just its length, and the length is calculated, with a formula like this for 2D, hypotenuse of a right triangle, or this in 3D, which is just extending it to the third dimension. So you see, I use the norm again on this next slide. This is a dot product, and we'll see this in the derivation that we do for the camera transform. And so the dot product is an operator that takes two vectors, A and B, and it produces a single number. And so there's a formula for the dot product that says you take the x components of the two vectors and multiply them and add it to the y components of the two vectors. And if it's in 3D, then you do the same thing and also add the product of the z components of the two vectors. And the dot product is really cool. The physical interpretation of the dot product is that it is, if you have two vectors A and B, the dot product is the cosine of the angle in between them times the norms, the lengths of the vectors. And so if you have sometimes so-called unit vectors, that's when the length is 1. So if the length of the vector, if it's a unit vector is 1 and 1, then these two terms drop out. And you just get, if you're dealing with unit vectors, that the dot product between two vectors is the angle between them. And so here's a vector A and here's a vector B, and then the dot product is the cosine of this angle in between them. Very useful operator. Similarly, the cross product is a very useful operator. And so here in the cross product takes two vectors, and then the output of the cross product is another vector. And so now we have a third vector, which we'll just call A cross B. And so the x component of this output vector, here's the formula for doing it. You take the y component of A times the z component of B, and you subtract the z component of A times the y component of B. And then similarly, here's the formula for the y component and the z component of the cross product of these two vectors. And you can see it's a little tricky that I'm switching the order up AB, AB, BA, BA, AB, BX, AZ, BZ, AX. Yeah, okay, that's fine. So BA, and then probably I wish I would have written this BA, but whatever. I still believe that's correct. And so anyway, so this is just a formula, and it's a formula for taking two vectors and doing the so-called cross product. It creates a new vector. But it also, like the dot product, it has a physical interpretation. And so if you take the cross product of two vectors, then it finds a new vector that's perpendicular to both A and B. And we're going to need that as we set up our camera frame. Okay, so some more discussion of homogeneous coordinates. This was something that I didn't really understand as an undergraduate, and to be honest, I don't understand as well as I probably should now that I'm the instructor for the course. Homogeneous coordinates are a system of coordinates. That's easy. It's used in so-called projective geometry. I know the first time I taught this graphics class, I did a lot of reading to understand it better. And really, most of what you find on the internet is there's two purposes. One is the one we want. We only care about the first. Graphics, 4x4 matrices to represent general three-dimensional transformations. And we talked about this on Thursday, that there's this trick that if we want to do certain transformations on three-dimensional points, we actually need to go into a 4D space. There's another use of homogeneous coordinates. I'll read it. It says it allows a simplified representation of mathematical functions, the rational form, in which rational polynomial functions can be simply represented. That's not what we're after. What we're after is, for us, homogeneous coordinates are a trick that allow us to take three-dimensional points and do transformations, and the transformations we need to do are not possible if we have just 3x3 matrices, but if we use 4x4 matrices, it'll let us do some neat things. And in particular, as we get into the view transform, we're going to have that moment, and you saw it in the last video, where we add perspective, where things that are close get bigger and things that are things that are further away get smaller. And these 4x4 matrices allow us to do that very efficiently. So homogeneous coordinates are 4D points. And so typically, and we talked about this on Thursday, we're thinking about three-dimensional points, and we're writing x, y, z, and now we're adding a fourth dimension, which is the w coordinate. And so for us, and for all the points we're thinking about, it's x, y, z, and we have a w value of 1. But what's going to happen as we apply our 4x4 matrices is sometimes these matrices are going to transform the point, so it's no longer having a w value of 1. And so then we have to figure out how to pull it back so that the w value continues to be 1, because that's the three-dimensional space that we want to render. And so this picture is actually visualizing this as a two-dimensional space, where along the horizontal axis we have x, y, and z, and along the vertical axis we have w. And so for us, all of our points are going to be x, y, z points where we have a W value of 1. But again, when we do our 4x4 matrix transformations, they will sometimes knock these points off the W equals 1 line, and we need to have a plan for treating those points. And so this slide says what our game plan is going to be. We're going to project it back to W equals 1. And so assume that we have a point that's been knocked off the W equals 1 line. So it's a 40 point where W does not equal 1. Our goal, again, is to project it back. We want to find a new point, P prime, with components X prime, Y prime, Z prime, but a W value of 1 such that P projects to P prime. And of course, that's easy to say, but we have to define what a projection is in this case. What does it mean to have a point that's off the W equals 1 line and to project it back onto the W equals 1 line? And so here's some words that describe the idea for the projection, and then there'll be a slide in a moment. The idea is we draw a line from P to the origin, and then we figure out where that line intersects with the W equals 1 line, and then that intersection is our projection. And so here's a picture of that. Here's the words again. If we have a point that's off the W equals 1 line, we draw a line between that point and the origin, and the intersection with the W equals 1 line is our projected point. So for example, we could have said our projection is just to drop it straight down. We're not doing that. Dropping it straight down would be the equivalent of discarding this point. Instead, as we project, we're bringing it back towards the origin. And so then there's some question of what is X prime and Y prime and Z prime, and that's pretty straightforward. There's just a similar triangles argument that says that X prime, Y prime, and Z prime is just these three numbers, X, Y, and Z, divided by W, because this triangle here is similar to this bigger triangle. And so this is how we're going to do our projection back, and this is actually really important. Pause. This is important for implementing the project. Whenever you take a point and you apply a matrix to it, it needs to be a four-dimensional point. It needs to be a point that is some x, y, z, 1. And when we apply the matrix, we're going to get some x, y, z, w. And if w is not 1, we can't deal with that point. We only deal with the points where w is 1. And so we need to follow this plan where we divide by w so that we can get it back to this which is the space we actually deal with our normal three-dimensional space. So the point being, after you do your matrix transformation, after you take a vertex of a triangle and apply the composed matrix M to it, you'll get as an output a 40 point x, y, z, w, and the very next thing you do is divide by w to get some new point x over w, y over w, z over w, 1, and that's the point you work with. Okay, so I'm going to stop. This is going to be part 2 of the video, and then part 3 will pick up on the camera frame.